All right. Hello, everybody. Welcome back for another algebraic geometry seminar. We're on lecture 6 now. And today we will be introducing the main character of the rest of this lecture series. So we will be talking about affine schemes. And the way that we will do this is last time, if you recall, we defined that a scheme naively was, I guess, a scheme on R. A ring was the data consisting of a set of prime ideals, which we denoted spec R. These are the ideals in R, which are prime. And for most cases that we care about, you can take this to mean that they're generated by irreducible polynomials, if we're working over a polynomial ring R. Then they consist of the topology that we will define today, called the Zariski topology on this set. This will be distinguished open sets. DF. And then the structure sheaf, which kind of the point of today's lecture is to prove that this is in fact a sheaf.
And what is F here? Like an element of R, or?
Yeah, so F would be an element. Yeah. Okay, so before we get too much further, last time I had said that I would talk about generic points a little bit more, and this will kind of make more sense today once we talk about the Zariski topology. But I want to go ahead and say a few things that will kind of set up the point of the Zariski topology and the idea of generic objects in geometry. So by Hilbert's Reichenl-Stillensatz, we know that the traditional points of a variety, or the base field, are present in this set spec R. Namely, we have these zero-dimensional things corresponding, like in the case of AN C, which we defined to be spec C x1 to xn. In this case, we have our traditional points in Cn as these maximal ideals, which look like x1 minus a1 through x1 minus, or through xn minus an. And then this would cut out a point P. So we know that we have our traditional points present. We also know that we have these kind of other pieces floating around of varying dimensions. So you have k-dimensional pieces floating around as ideals that look like cutting out k many curves. And I'm going to say that this capital X that I'm using is just x1 through xn. That's just an abbreviation, so this doesn't take up the entire board. And then we also have these maximal dimensional things, so these n-dimensional pieces, which are called generic points. And in the case of an affine space, this is exactly one point, which is the zero ideal. And so the idea is that over every irreducible subset, and specifically once we define what a closed set is, over every irreducible closed subset, there lives this generic point whose Zariski closure, and again a word we'll define today, is exactly equal to that irreducible closed subset. I.e., really, this ideal is contained in everything, in every ideal in spec Cx1 over xn. So similarly, for other generic points, if we have a quotient ring cx1 through xn mod I, over every irreducible closed subset of that, there's going to live a generic point whose closure is that subset. And then we'll have the property that that ideal corresponding to the point is contained in every other ideal in that closed subset. So this will give us a way for dealing with generic objects and specific objects in geometry and specifically intersection. This is like a valuable idea. We won't talk a lot about that today, but when we get more into the geometry behind algebraic geometry, once we finish defining all of our machinery, this will be an important idea. Another observation that I want to make real fast. So previously we talked about the radical ideal and Hilbert's Milstellensatz. We defined that if I was an ideal in a ring R, then the radical ideal of I was the set of A in R such that there exists an integer with A to the n in I. Scheme theoretically, what this is going to be is this is going to be the intersection over some indexing set. We'll use J. I is taken of all of the prime ideals containing. This is the intersection of the prime ideals containing I. So no, J contains I and J. Spec. I'm going to state this without proof, but this is maybe something that's helpful to work out on your own. Is that this intersection of prime ideals gives you exactly the radical ideal, and that there's a relationship here to generic points. Okay, so with these preliminary notions out of the way, I want to go ahead and talk about a base for Zariski closed sets. So essentially, we want to be able to come up with closed sets, and then we want to be able to figure out what open sets in the Zariski topology look like as our means of defining it. Okay, so for the Zariski topology on varieties, we defined it by saying that open sets were the complements of roots of polynomials, or zero sets of polynomials. We'll define something analogous, and we'll kind of wind back this definition in a way that makes sense. So let S be a subset of a ring A. We will define the vanishing set V of S to be the set of points in spec A. So the set of prime ideals such that S is contained in prime ideal V. So namely, this is, in plain English, the set of points of the scheme which, on which the functions in S vanish. Okay, so this is looking like our closed sets from the ordinary Zariski topology, and it turns out that these are our closed sets for the scheme theoretic Zariski topology. So we will take, arbitrary subsets of our ring, and we can define closed sets this way. And then open sets, naively, Zariski open, is going to naively mean S complement. It is true that this is true, but we're going to define kind of a nicer base to work with to really do algebra on the ring of functions that we'll define on spec A. So as an example, before we get to that, of these closed sets, we can consider the vanishing of x, y, and y, z in A3C which again, just recall, is spec C X, Y, Z. And so we can think of this set as the solutions to the equations x, y is equal to y and z is equal to 0. But really what this is going to look like is it's going to look like the y-axis, and it's going to look like the xz plane. These are our kind of conventional points in the sense that you have to have either y equals 0 or x and z equals 0. But then, scheme theoretically, we also have these other points floating around. We have our k-dimensional points. So we're going to have cut curves. So these are our zero-dimensional components. We have the generic point of the y-axis and the xz plane. These are two-dimensional components. Or, sorry, three-dimensional. And then we're also going to have all of our curves in between. So we can have finitely many, let's see. Yeah, we also have one-dimensional ideals contained within the xz plane.
Wait,
So we'll have.
Question. Sorry.
Yeah.
So how did you get zero-dimensional for the y-axis and the xz plane?
Because they're going to look like points. So I guess, yeah, this is maybe, yeah, this is sort of for wording. Points on yeah, and so this is going to look like stuff of the form, x minus a, y minus b, z minus c. Well, of course, for it to be on any of these things, you need certain conditions, right? You can have all of the ABCs 0, and then you're corresponding to the origin, which is the point of intersection of the y-axis and the xz plane, or you're going to have, this corresponds to the y-axis, this corresponds to the xz plane. As the generic points, well, then you're going to have, if you want it to be along the y-axis, you're going to vary your a and your c, and you're going to have b equals 0. Similarly, if you want to go along the xz plane, you can vary your y, you can vary b, and that's going to move things around that way. So these are the genuine zero-dimensional points. The generic points are the entire axis or the entire xz plane. And then you're going to have curves on the xz plane, which are going to look like f of x, y. Okay. Yeah, these will be one-dimensional. Keeping in mind, you can cut out points that are, you can view points that lie in the xz plane as an intersection of two curves. And then we would say, well, yeah, you could have surfaces that are two-dimensional, but for you to have a surface, you would have to have the entire xz plane contained within it. And so then we're going to kind of eliminate the idea of a two-dimensional subscheme. And so then we kind of get this zero-dimension, one-dimension, and three-dimensional piece. And then the second dimension is kind of empty. Well, I guess maybe empty in the set that the xz axis, or the xz plane lives there. So it's not actually empty. Is that clear?
Yeah.
Okay. Awesome. So I want to make an observation real fast about this function v of s. So v of s end up actually being equal to the variety, or not to the variety, to the vanishing of the ideal generated by S. And so the idea is that V is order is inclusion reversing. So this is kind of going to be property 1, but really property 2 that you can state first is if S1 is containing S2, then you end up getting that V S2 is contained in V of S1. And so this ends up being kind of useful to show that this first property is true. Namely, if you are given a prime ideal in spec A that's in V of Vs, right? So V in Vs, well, okay. What does it have to do? It has to be containing S. So P contains S. I guess maybe we should put these brackets here. It's more notational than anything. Okay, so since P contains S, then the ideal P contains the ideal S. So P contains P ideal generated by S. And so then, of course, P is in the vanishing of the ideal. And I guess this is maybe poor notation. I should be consistent with that. So this is kind of the first inclusion for 1. The second inclusion follows in a similar way. You pick a maximal ideal in the vanishing of the ideal generated by S, and you get something similar. Okay. So we're going to, we've defined open sets, we've defined this inclusion reversion. Yeah, we're going to also give an example of, so I guess this is a closed set, right? So this was our example of a closed set. Now let's talk about what open sets look like in affine 2 space, so in the affine plane. And in this case, we'll just give a general characterization, right? So an open set that would be a complement of this would be the complement of the y-axis, the complement of the xz plane, the complement of their respective points, or the complement of any curved line in the xz plane. Any of those could be an open set of this form. Okay, so topology of A2C, which again, spec C. This one. Okay, so in A1C, and I'm going to start with A1C, and then quickly erase it. It's boring. So A1C is spec C XY, and an open set U is going to look like the complement of the vanishing of some subset of CXY.
Wait,
right?
so wait, A1 is spec C of XY or just spec C of X?
Oh, very good point.
Yeah.
Yeah. All right. Good errata. Okay, so we'll have S is going to look like something in C over X, so it's a polynomial f of X, maybe indexed in some way. Right, so we can take infinitely many, countably infinitely many polynomials in C of X, and we can call this S, and we can take the complement of their vanishing. So B of S is going to look like all of the points spec A, such that P is, S is contained in P. Okay, so the idea here is that we have a relationship between these functions being contained in prime ideals and vanishings of the functions in S on the points P. And I'm gonna write this in text because that's maybe the most valuable thing to take away from this. For practical use is that the points. Yeah. So F in the vanishing of S. No. No. Sorry. You can tell that this is the unscripted part.
It's all good.
Vanishing at point spec A is identified with, so a function f in A, vanishing at a point of spec A, is the idea of f, I guess maybe a point E, spec A, is f is a function contained within P. Okay, so the idea then of S vanishing is that, well, S contained in A, which is Cx in this case, vanishing at a point in V of S is really the idea that F is already in this ID. And so what the complement of this set is going to look like, since the vanishing of polynomials in one variable are points, what this is going to look like is going to have, it's going to look like the affine line minus finitely many maximal ideals. Sorry, PI. i.e. it's going to look like irreducible points x minus AI. So this is why we say that the affine line is somewhat boring. Is that the affine line is implicitly kind of just complements of points. So this is the big idea with A1C. Now we'll talk about A2C, which is a little bit more interesting. Any questions at this point?
So that was a countable collection of polynomials that you had there?
Yeah.
Okay.
Okay. So with A2C, we're looking at the prime ideals of the polynomial ring spec CXY. And we've previously defined that all of the prime ideals are of the form of zero-dimensional points, x minus a, y minus b, one-dimensional curves, which are going to look like f of x comma y, or two-dimensional generic points, which are going to look like, let's see if the double bracket is not necessary. Okay. So this is our generic point. Okay. So then our closed subsets are of the form of the entire space, which is the closure of this. So entire space. Which is it's going to look like a finite number of curves. I guess really this is for a finite number of curves, possibly 0. And a finite number of points corresponding to maximal ideals. Possibly 0. So the idea is either it's the entire space or it's a combination of curves and points. So for example, you could have 3 curves that look like so, and you could have 3 points, and there would be 6 closed points in the scheme, but this is a perfectly valid closed set. And then the complement of these points and these curves would be an open set in the Zariski topology on affine Q space. Yeah, the key idea here that makes this possible is that if f and g are 2 irreducible polynomials, their zero sets intersect finitely, and it's bounded actually by the degree, or by the product of the degree of the polynomials. This is something that we'll talk about later as topological Bezout's theorem, but the idea is if around the inflection points of the curve, of each curve, you assign a tangent vector, and you let this go for each curve and intersect all of the other tangent vectors, then for these curves, the tangent vectors are going to cut each other as many times as you have inflection points, which is determined by the degree of the curve. This gives you a form of Bezout's theorem called topological Bezout's theorem, where you can count the intersections of plane curves as intersections of their tangent vectors. And so there's some nice dimensionality arguments you can make here. We'll have a whole lecture on Bezout's theorem. So this is kind of one of the big things in algebraic geometry that motivates why we use all this machinery. But it also gives us the fact that you get these finite number of curves and finite number of points. Another way of viewing this for the finite number of points is that you can view a point in the plane as the intersection of 2 curves. And so then you can do the same tangent vector argument, provided that you're not thinking of these as maximal ideals, but you're thinking of them more as intersections of curves which correspond to maximal ideals. There's something that's in the radical ideal, or like the maximal ideals would be in the radical ideal. So anyway, this is kind of the geometric notion of what's going on here. Any questions on this? Okay. So, as a final remark, or no, I have 2 final remarks. It was kind of funny. I was writing my lecture notes somewhat last minute, and I put in, it's a final remark, and then I had a second final remark. So if you look in the notes right now, there's 2 final remarks for this section. So as one of the final remarks for this section, we recall that last lecture we had said that maps of rings, so if you had A to B, and I'm realizing I'm going to switch these. If you had a map from B to A, rings, then spec gives us a functor sets that's contravariant, meaning that we can induce maps of spectra with maps of rings. And what I'm here to say today is that, well, if this is phi, then this is phi star, it's the pullback. This actually is a topologically continuous map. So this is going to go to topological spaces. So this will give us a morphism of spectra that is consistent with the Zariski topology. And then once we define the structure sheaf, this won't just be topological spaces, but rather schemes. The idea is that we're sending prime ideals to prime ideals in the map of rings. So we're sending, P to 5P, and then this induces a natural inverse, where we're sending inverse images of prime ideals or prime ideals. And then that's sending closed points to closed points. So it's a topologically continuous map. And then accordingly, of course, taking complements and applying De Morgan's laws, inverse images of open sets are open. Okay, it's also worth noting that not all continuous maps are constructed this way. So we have, there's a kind of cool example. The continuous map from affine 1 space the affine line to the affine line, sending a point. I'm going to just describe the image. It's going to be the identity, so 1 if x is not equal to 0 or 1, and then it's going to be 0 if x equals 1, and 1 if x equals 0. And I'm realizing there's something redundant here. So if x is not equal to 1, then we can get rid of this line. But this is something that is, in fact, a continuous map, and that no polynomial can actually achieve. And so the idea is that you can get continuous maps of schemes that are not polynomial maps, and that we're going to be rather interested in the polynomial maps of schemes. And this is something that we'll talk about more next lecture or 2 lectures from now, because I haven't decided if I'm going to talk about quasi-coherent sheaves yet. Next lecture, the topic might vary. We'll see. Okay, so now the final remark of this section is that, yeah, the Zariski topology plays nicely with quotients and localization, which we spent the better half of last lecture talking about. So if you let I and S be contained in B, where I is an ideal and S is a multiplicative set, then we have the following properties. So 1 is that spec of the quotient B mod I is a naturally closed subset, spec B. For the second property, and I use this to say closed set, I have a similar notation for open set where there's an open bubble above the subset, so just for people tuned in. And then if S looks like a localization at one polynomial, then spec of S inverse B is a naturally open subset of spec B. And we can geometrically think of this as just being functions away from the vanishing of F. And so naturally this is defined by the complement of the vanishing of F. Okay, so then if S doesn't look like this, but is some other multiplicative set that's not generated by one polynomial, then it's going to maybe not be open, maybe not be closed. It just depends. You can take, 1 F G F squared G squared. That will be open. That's the intersection away from F and G. But if you take, 1 F G G squared and just leave all of the higher powers of F untouched, maybe it won't be open. So it's just something to chew on. All right, any questions about this before we move on? All right, so now we've talked about a base for the Zariski topology and closed sets in the Zariski topology. Now we're going to talk about a base for the open sets of the Zariski topology. So in the same sense that we've constructed closed sets and we've said open sets are the complements of closed sets, we're going to define these things called distinguished open sets. And the reason why we call them distinguished open sets is that they're distinguished by a certain polynomial in the original ring. So if you have F and R, we're going to define dF to be the set of prime ideals P spec R such that F is not in P, or equivalently, this is the set of prime ideals in spec R such that F evaluated at the ideal is as it turns out, this forms a base for the Zariski topology. So namely, if S is a subset of A, then for every vanishing complement, it's going to look like a union over the things in S of the DFs. So we get this base, and now we have some properties of the base that are kind of nice. And there's one property that I wish was in here that we're going to use a lot in the proof that the structure sheaf is in fact a sheaf. So I'm going to try and state it from memory. I'm going to point out something else. In the sense of compactness, spec A is quasi-compact, meaning that it's not necessarily Hausdorff, but every open cover admits a finite subcover. And this is a fact that we're going to use quite a bit later on in the proof of the structure sheaf being a sheaf. And then that's going to motivate one of these facts. So, okay, so fact. Number one, the intersection of two distinguished open sets is the distinguished open set of the product of the polynomials. And geometrically, this is exactly what you would want to happen if we want this to line up in terms of the conventional points of the scheme. So if we're thinking just over the base field Cn, in An, if you have two functions from the original ring and you're evaluating them on these conventional points, well, the complement of the zero locus of one of these curves is going to be the union of the complements. So geometrically, this works. Okay, second fact. So if one of these distinguished open sets is empty, then, and it's really an if and only if, F is in the nil radical of the ring. So recall that this is the radical ideal of 0 in the ring. So these are all of the functions F such that F to the n is equal to 0 for some n. So this is our idea of nilpotence. When we talked about generic points at the start, what I kind of was avoiding is that, and this is something that I do want to say, so if I is an ideal of nilpotence, and an easy example, a way to come up with this is spec A mod some ideal G, and G is a function in A. Say EG. And if I is an ideal of nilpotence of A mod G, let's say, then it actually turns out that you can get A mod G, we're going to call this R. Then R, spec R mod I, is actually isomorphic to spec R. I'm going to state this also as a fact. It's just a cool fact, so I'm not going to prove it. But if you do prove it, it's a lot of fun. Okay, and then this motivates why the distinguished open set of a function is empty if and only if it's in the nil radical. It has to vanish on everything because it has to be generic to that closed irreducible subset that it's in. So if you have a function on a closed irreducible subset that vanishes on everything, it has to be in the nil radical because it vanishes on everything. Okay, and then our final one is also a cool fact related to the nil radical. So one distinguished open set is contained within another if and only if F is in the radical ideal of G, or rather f to the n is in G, for some n, if and only if G is an invertible element of the localization of A at F. And this last, like maybe this part seems fine. This last part might seem a bit tricky, but we can talk through it. So we have the following construction. I'm going to erase this piece. No, I'll erase this piece. So the construction is this. So let's say that we have the closed subset in spec A mod G, like we did before. We'll call this R. This is closed by one of our previous facts in spec A. So we have the closed subset, no, I guess not R, but we'll call this V of G. Well, V of G is a closed subset in spec A, and so its complement, V of G complement, is where G fails to vanish. So then F is a function, non-vanishing, on D of G, on V of G. And by assumption, it vanishes at all closed points of the closed subset. And so the idea is that it's a function of vanishing. Now, from fact 2, any function vanishing at every point of the spectrum of a ring must be nilpotent. And as we've said, V of G is in fact the spectrum of a ring, A mod G. And so we have that, in other words, there exists an N such that F to the N is equal to 0 in A mod G. And what this means is that F to the N is equal to 0 mod G, which is equivalent to saying that F to the N is in the ideal G for some N. And so now fact 3 is proven. Okay, so these give us a good intuition for the structure sheaf. Now I want to make sure that we have time for this proof, because your time is valuable. So I might run through some things. Oh, damn, I didn't say the fact that I meant to state. It's fine. When it comes up in the proof, I'll say this is the fact that I meant to state. That's okay with you all.
It's fine.
Its proof is...
I said that's fine.
Okay, cool. Okay. I suppose I should maybe give one example of what the structure sheaf is meant to accomplish. So the structure sheaf is meant to pair together our open sets, or distinguished open sets really, and functions defined on them. And the natural pairing is, of course, F and B of F. So this is consistent with what we saw with algebraic varieties and what you would see in like Hartshorne chapter 1, where O of X, or O of, in this case, spec A, would be the set of these functions, where F is A. So this would be one way to define it, and this is a perfectly valid way to view the structure sheaf. Kind of the example that you would maybe want, that in A2, to have an algebraic function, and more specifically a sheaf of algebraic functions on it, you could have that dxy is the set where x and y don't vanish. F A such that F is not contained, or F is not in times P, which are in vanity of x. We should expect that a function like 3x to the fourth plus y, minus x squared y over x to the third y to the seventh should be well defined as algebraic on the xy because it has a denominator. And this is true because we're not divided by 0. So this is an algebraic function. This is what things are going to look like. Now, it's worth noting, these functions have values at points, but they're not determined by values at points. They're determined by values of germs of the open subset dxy. So going back to when we talked about sheaves, a germ is like a shred of a given function in the underlying topological space at that point. And so what we're going to look at is we're going to look at these shreds as ways of determining equivalence classes of functions around points and around these dxy, or like dfs, or generally distinguished open sets. Okay, so defining the sections of the ring of algebraic functions, the sheaf of algebraic functions. So the sections of the structure sheaf are as
Quick
follows.
question. Sorry.
Yeah.
So you just wrote down kind of a rational function, right?
Yeah.
Yeah, so that's not an element of the ring itself, right? Like C of xy.
Yeah. So that would be an element of the ring. Yeah. Because that's a function on the points of the scheme.
Oh, okay.
Yeah. So functions live in the original ring, points live in spec of the ring.
Mm-hmm.
And then the sheaf of functions are going to be algebraic functions whose denominators are non-vanishing on the points of the scheme.
Got it.
Yeah.
Okay.
It gets very confusing. There's a line in Vakil where he quotes, I think, F. Scott Fitzgerald, where it's like, a sign of intelligence is that, someone can hold two diametrically opposed ideas in their head at once and not go insane. And this is very much one of those things where it's like, okay, which one am I working with again? So.
Okay. No, thanks.
Yeah.
That clarifies it.
Yeah, this is where the example of spec Z I find really useful because it's just modular arithmetic. So you know what functions are and you know what points are. I think I said that on day one of sheaves, but yeah. Anyway, okay. Any other questions? Okay. So we're going to define the sections of O spec A as follows. We're going to look like O spec A over some open set df, and it's going to look like there's two ways to present this. So either the localization at the set S, where S is functions f in A, which are not vanishing outside of df. Or we can define this, and I think that this is maybe more clear, as the set of functions g in the ring A, such that the vanishing of g is contained within the vanishing of f, and an equivalent statement to this is going to be that df contains dg. And again, this is a property of the inclusion reversing of V. So, namely, this depends not on F, but rather on the open set D of F. And so in the sense where there are functions F that it does depend on, but those are going to be the germs that we look at to determine functions. Right? So if it doesn't depend on F, then it's going to look like something that is shared by the germ of F. And so we're going to want to classify things in terms of these minimal Fs, or maybe minimal is not the right word, but irreducible Fs. They give us these nice properties. Okay. I'm also going to highlight something, and this is maybe something to work out at home. The localization of A to F is actually an isomorphism to the section of the structure sheaf over D of F. We're going to use this quite a lot in the upcoming proof. But yeah, this is an isomorphism. Okay, I'm going to also, so these are sections, existence of sections. We also get restriction maps, so then we get a pre-sheaf. So the restriction map from, we'll say df to df prime works the exact way that you would hope that it would, namely passing through this isomorphism, we can pass back to this AF and further localize AF to AF prime. And so then you're kind of restricting down your DNF to a larger DNF. So this is the idea of a restriction map. Clearly restriction maps commute because they work in kind of the way that you want them to. And so we have a pre-sheaf. So the structure sheaf is, if nothing else, a pre-sheaf. Now there's a joke that my topology professor loves, which is that, well, a sheaf is just a pre-sheaf with the sheaf axiom. And it's very true. And yeah, we're going to prove that this has the sheaf axioms on it. This is going to be kind of the big thing today. So again, we're going to call this O spec A the structure sheaf, and then we're going to call spec A an affine scheme. So when I use these words, what I really mean is spec A is endowed with the structure sheaf. So if I write spec A, we're going to prove today that it always has this object, and then is thus an affine scheme. All right, let's get into the proof of the identity. So recall that for a pre-sheaf to become a sheaf, we want to show that there is at most one way to glue functions on open subsets. There's at least one way to glue functions on open subsets. And so that's what we're going to do now. So this first one is identity. So suppose that spec A is equal to a union that is necessarily finite of DFIs, finite because of quasi-compactness of spec A, and so Noetherian. This is something that can be proved, but that we'll take for granted right now. So then we have really that A is equal to the ideal F1 to F. Okay. So suppose now that we are given S in spec A with the restriction map of spec A to DFI of S is equal to 0 for all, and 0 in the localization at Fi for all I. And what we're saying is that we have local behavior that's consistent, and what we're going to try and show is that there's no other way that we can glue functions on this section and not get a global section, and not get a global function. Okay, and then also it's unique. That's the key piece. Okay, so so we want to show that S is equal to 0, and that will prove this. So the existence of this restriction map gives us that there exists, and I'm going to bar that so that this doesn't look like this thing implies this thing, because that would be circular. So we're given from this fact that there exists in M such that for each I in 1 to n, we have Fi to the M of S is equal to 0. Okay, so then it follows that since f1 to the m through fn to the m is also equal to a, there exist ring coefficients Ri in A, with the sum I equals 1 to n of Ri Fi to the m is equal to 1 in A. This is the fact that I wanted to say earlier but didn't have in my notes. We're going to take this like it's true, and maybe I'll post an errata in the comments or in the notes. If you care about the proof of this, you can check Wiki or my notes. But we're going to use this fact a lot, so I really wish I'd put it in there. Don't procrastinate, kids. Okay, yeah, this is given in McKeel chapter 3, section 3.3. All right, so from this, we get that S is equal to 1 times S, which is equal to this formal sum times S. I equals 1 to n, Ri Fi to the m times S. But this is equal to, we can associativity things around, and then this is equal to 0, which means that this whole thing is constant. And so then we have that S is 0 globally. Further, you'll note that we're doing this for the entire scheme, we're not doing this for local sections. So if we wanted a local section of our structure sheaf, what we would do is we would say, well, we can restrict A to its localization at a section defined by some polynomial f. And we can take spec AF is similarly equal to its finite stratification of open sets. And then the rest follows. So we have identity. That part's done. I don't have much time left, so I'm trying to get glueability. We'll assume the case of finiteness. There's an infinite version of this that you can do an induction proof for, but I wouldn't recommend it. There's instead something called the extra equalizer exact sequence, and if you prove that that's an exact sequence, then you've proved both of these conditions. That's what I would recommend for the infinite case on glueability. So, and I guess maybe I can trace a little bit more. Okay. To check glueability, we're given the same thing. So say that we're given elements in each section on Fi that agree on overlaps. Which are co-localizations AFI, FJ. No, sorry, maybe co is a bad word. That has a technical meaning. It's the intersection of the sections over Fi and Fj. Okay. So, kind of the note here is that intersections of distinguished open sets are in fact distinguished open sets, since this is finite. So we're going to have these elements be Ai over Fi to the Li in A, Fi, agreeing on these overlaps. So we're going to let Gi be this Fi to the Li, but we're not going to forget that it is Fi to some power. And then the fact that Aigi agrees with Aj Gj gives us this formula that there exists some Mij such that Gi, Gj Mij times Gi, Gj minus, not A, GIAJ minus GJAI is equal to 0. This comes from setting equalities and then multiplying and then finding an explicit m. This can be done in general for each of these functions, and mij is dependent on li and lj. So that's why we're kind of getting rid of those things. The important thing is that mij exists and that we get this formula. Well, we'll let m equal the max of these mij's. And then this is going to give us a global property that for any ij, we have this formula. Well, we can further simplify things down by saying that bi is equal to ai di to the m, and hi is equal to gi to the m plus 1, so that the distinguished open set of hi is equal to the distinguished open set of gi. And so then, on each distinguished open dhi or dgi, there exists a function bi hi rational with an equivalent overlap condition to this, that hj bi is equal to hi bj. So now, passing down this finiteness condition on our affine stratification of spec A, we also get an affine stratification in terms of these hi. So we have that spec A is equal to this stratification of dhis. And then we're going to use the fact again that I really want to have stated, but that there exist ring coefficients Ri times hi, so that we get this equal to 1 for some Ri. So now we'll define R as the sum I equals 1 to n of Ri bi. I'm going to claim that this is our global function on all of spec A that restricts down to our AFIs and AFJ sections uniquely. So this is our at most one way to glue. And now we'll prove it because it's short. So namely, R times Hj, which is our criterion for restricting us down to the jth component, is equal to the sum I equals 1 to n of Ri bi Hj. Well, this is equal to, by previous assumption, the sum I equals 1 to n. Sorry, yeah. This was meant to be j. This is going, since bi is equal to bj on the overlap, we have Ri bi Hj. Nope. This is j. This is j. No. Yes, there we go. Okay, this is fine. Bi. No, we want this to be bj. This is going to be hi now. There we go. Sorry about that. And then we can pull this out. We can pull out bj by linearity and get Ri hi, but this is equal to 1. And so then Rhj is just equal to bj on A. And so now we have gluability. This is for a finite partition. There's again a way of doing this for infinite partitions. You can do the same localization trick with A to AF. However, I wouldn't recommend it. It's just nasty subscript stuff. This was already pretty bad. It gets much worse in the infinite case. I recommend just proving the exact sequence that's stated in Vakil 3.2 or 3.3. All right, so yeah, the structure sheaf is in fact a sheaf of algebraic functions on spec A. Spec A is an affine scheme. This is what we're going to be working with for the rest of the lecture series. And yeah, are there any questions before we stop the recording?
Nope, no questions for me.
Well, thank you so much for your time and attention. And just as a note, there won't be seminar next week because I'm on a road trip. So I will be somewhere in, I think, Nashville this time next week. But we will resume in 2 weeks.
Alrighty, sounds good.
Cool. Thank you so much.